Por el camino del desierto, el viento me despeina, suave aroma de colita, nada del área.
So, point 2, we're going to look at the short run behavior. So we have our f of x is equal to an x plus 3 times x minus 2 quantity squared times x plus 1 quantity to the third. Okay, so for short run we have to first of all identify what are our zeros. Okay, so our zeros or our horizontal intercepts occur at x equals negative 3. They occur at x equals 2. And they occur at x equals a negative 1, right? So, and at negative 1. So the thing is here, once we find our zeros or our roots, we want to kind of split them up into their own like categories and study what happens at each of those roots, right? So let's see, x equals negative 3. I'll put x equals negative 1 here, and then x equals 2. Okay, so if we look at the x equals negative 3, let's look at that grouping that gave us that. So if we look here, we see that the power on the grouping is just a 1, okay? So that means, when we're looking at our roots, this means that as we cross through the horizontal axis at negative 3, we should have some kind of linear graph, okay? Something that looks like either that or looks like that, because we have the power of 1, right? Where on the other hand, let's say we're looking at the negative 1, right? So this is the negative 1 grouping, right? And we see that there's a power of 3 on it. So let's say here's the horizontal axis, the x-axis, right? Here's our negative 1, that's where we're at. And this is going to be a cube, that's like a cubed function, right? So it's going to look like an S as we get close to that 0 there, okay? It kind of resembles a cubed graph, right? Our parent graph there. Okay, and then the last one, x equals 2, let's look at that group, which gives us this one, and that has a power of 2 on the group there. So that means as on our x-axis, as we get closer and closer to the root of 2, then it's going to look like a parabola, right? So it's going to look something either like this, facing up like that, or it's going to look something like this. And that's determined by the long run behavior, which one it is, okay? So let's put everything together all on one graph, okay? So let's say we have something like this. Okay, so here's our x, and here's our y. Let's say this is negative 1, negative 2, negative 3, negative 4. 1, 2, 3, right? So we have negative 2, negative 4, and a 2 here. 1, 2, 3, 1, 2, 3. Okay, so let's just graph our roots for now, our zeros. So we know there's a 0 when it passes the x-axis at negative 3, negative 1, and positive 2, okay? And from part 1 on the last slide, we know as for the long-term behavior, or the long-run behavior, overall our function takes on like the behavior of an x to the 6th graph, which means it has to go up on the left and up on the right as x goes to positive infinity and to negative infinity, right? Something like that. Okay, so that takes care of the long-run behavior, and now we have, okay, so let's just fill in our spots. So at x equals negative 3, so this guy right here, we want some kind of linear crossing of the graph. So it has to look like a line, and it has to have a negative slope, because if we were to put something like this, that would mean to get from this part to this part, we'd have to cross the graph. But we don't have any other intercepts, right? So that means that we have to have that negative slope, or this negative crossing at negative 3, at the root of negative 3. Okay? So now, let's look at negative 1. This one right here, okay? If we look at that 0, when we pieced everything apart, this should look like some kind of S graph, right? It could either go this way, or it could go this way as well. Either one. But let's see what it should look like. So, we're down below the x-axis down here, and there's no other intercepts, so it has to come from below and kind of look like this one right here. Okay, so that's like our x cubed graph kind of thing. Okay, and then now let's look at x equals 2, positive 2, right over there. Okay, so we should have some kind of U going on, like where it, the graph touches the x-axis and then turns around and goes in the same direction, right? So here we see that, well, on the left of 2, when x is less than 2, then we have the graph is already up here, right? So it has to be up there to begin with and come down to 2. Down to x equals 2, and then go back up so it can go up to infinity for the rest of x, okay? So it looks something like this. Alrighty, and we just connect the pieces now, and this is generally what our graph looks like. Okay? Okay, so one last thing about that example that we just did. Let me write down the equation again that was given to us for the polynomial. Okay, so we had something like this, and you know how I said, well, when we look at each root, we're going to look at them individually, and then we're going to see, okay, what is the power on that group, right? Remember, we pieced everything apart. This is a power of 1, this is a power of 2, this is a power of 3. These are also called the term multiplicity. Multiplicity. Which that word, that term in a general sense, kind of just means how many times does that root occur, okay? Because, for example, if we were to write this all out without the powers and making them all 1, we would get x plus 3 times x minus 2 squared. If we actually write that out, we get x minus 2, right? So we can see that the root of 2 occurs twice, right? So it has a multiplicity of 2. Multiplicity, I'll just abbreviate, of 2, right? How about the x equals negative 3? That only occurs once, so it has a multiplicity of 1. Okay? And then if we were to write out the x plus 1s, we get x plus 1, x plus 1, and x plus 1. So we get the same root of negative 1, but 3 times. So that means that this has the highest multiplicity, and it is of 3. Okay? So you can see how the power on each of the groups corresponds to the multiplicity of that given root. Okay, let's do another practice of graphing a polynomial. This one again is already factored for us. So let's look at first the long run behavior. Okay, so to do that, we have to find what is our leading term. Okay, so we have f of x is equal to negative 2 sitting out in front times x plus 3 to the second power and then x minus 5. Okay, so if we ignore the constants, we should ignore this one, and this one, right? Not exactly. When I say ignoring constants, I mean the ones attached to x's, like the ones being added to the x or subtracted from the x. So these ones right here, this 3 and the 5, they don't really matter. But coefficients, meaning things multiplied times the x, constants multiplied times the x's or times your variable, those ones do matter and they're really important. So if we keep that negative 2, overall we're going to get that our leading term is negative 2 times x squared times x, which is the same thing as saying negative 2x to the third, okay? So what this means is that our leading term will look like this, and so we have a negative and an odd power, okay? So odd meaning it's going to look like some kind of s, and because it's negative, that means it'll be flipped around, so ultimately it'll look something like this. It'll go up on the left, as x goes to negative infinity, and down to negative infinity as x moves along to the right, okay? So that's what's happening on either end of our graph, something like this, okay? So that's our long run. I'll just write in long run behavior. Okay, now we need to find our roots so we can look at the short run behavior. Okay, so the roots of our polynomial here are, let me just write it down again so we can work with it. So negative 2, x plus 3 to the second, x minus 5. Okay, so from this grouping here, we get x equals negative 3 is a root with multiplicity of 2. Okay, and then from this grouping, we get x equals 5, a positive 5, which has a multiplicity of 1. Okay, so we see at this one, because we have a multiplicity of 2, it's either going to look like this at the horizontal intercept, or it's going to look like this at the horizontal intercept, right? And then this multiplicity of 1 means it's either going to look like this, or it's going to look like this, okay? Alright, so now let's get to making a sketch of our graph here. Alrighty, so let's say here's x, here's y. We have 1, 2, 3, 1, 2, 3, 4, 5. Okay, so our roots are here at positive 5 and at negative 3. We know on the left, because of the long run that we have already determined, the long run behavior, it looks like this and this, right? And then so we see, well, at negative 3, we should have a touch and turn, it's called. Basically, it just touches the x-axis and turns around, right? It doesn't cross it. Okay, so we have to have something like that here. And we know it has to be upward facing because the left part has to connect with what we've already drawn, right? And then we have it goes up probably, and then at positive 5, we need it to cross the axis. We need it to cross the x-axis, so it has to look something like that. So we're just going to connect it and make it nice and smooth. Okay, and there it is. That's a sketch of our graph. Okay, so now we're going to build off of what we've learned, and we're going to learn how to solve, or solving, polynomial inequalities. Okay? Inequalities. Alrighty, so how do we do this? We don't move the screen. Okay, so solving polynomial inequalities, that just means that some polynomial, some like expression for your polynomial, is either less than a, or is like greater than or equal to a, stuff like that. And then you just have to solve it. But it's like, how do you even solve that? So there's kind of a trick to it, right? So what we're going to do when we see a problem like this, some kind of polynomial inequality, we're going to treat it like an equation first. Like you just replace this guy with an equal sign, and then you solve for that. You find the roots and everything, and then we just work from there, okay? So let's do an example. I think that's the best way to explain. So here's a really great example that actually shows why you would even want to deal with polynomial inequalities, because they seem kind of unnecessary when you just hear the term, right? But the thing is here, so we're supposed to find the domain of this function here, okay? And we see that the outer function kind of thing, like the overall function, is a square root, right? Because there's a square root over everything. And the thing with square roots is that they must have some kind of non-negative value inside for it to be a real answer, right? So we want whatever's in here, some number, to be greater than or equal to 0. All right? So the thing is, when we do set that equal, so we have everything inside, so this 6 minus 5t minus t squared must be greater than or equal to 0. So thus, this right here is a polynomial inequality, right? Because we have a polynomial here, and we have some kind of inequality going on, right? So like I kind of alluded to on the previous slide, what we're going to do, the process for solving these, is to say that, well, let's just write everything down exactly as we see it, except for we're going to change that inequality sign to an equal sign, okay? And what we're going to do is basically just solve for the roots first and kind of pretend that this equality exists, okay? And then we're going to study what goes on. So if we look at this, what we can do first of all is just divide on both sides by -1. Just to make our lives easier, just to remove this -1 in front of the t squared, actually, okay? So if we rewrite this, and I'm just going to switch around the order a little bit, so we have t squared plus 5t minus 6, so I just divided by -1 and then switched the terms around, is equal to 0 still. That's the great thing about 0, because whenever you divide by any other number, it's just 0, right? Okay, so now if we factor this, we can get t something times t something something is equal to 0. So to get to a -6, we can use, well, like a +6 and then a -1 or something like that, right? So we find that our roots are going to be t equals 1 and t equals to -6, alrighty? So what our job is now is to see, okay, well, the first thing is we could graph this, or we could use another method to determine when is our graph. Because the thing is, let's say we have, we're at 1, 2, 3, 4, 5, 6. So we have a root here at -6, and we have a root at t equals 1, right? This is like the t-axis, and this is like our y, or our v of t-axis, okay? The thing is, we don't know if it goes like this or like this, right? I mean, we can determine it graphically, but I'm just going to show you guys another way to determine it without having to graph anything, okay? And I'll show you that method on the next slide.